Welcome back to the Deep Dive. Today, we're really getting into the nuts and bolts of modern tech. We're taking a close look at the fundamental quantum physics of semiconductors. Our guide, none other than Richard Feynman, specifically Chapter 14 of Volume 3 of his lectures.
That's the plan. We're aiming to bridge the gap, between the theory of quantum mechanics and crystals and how we actually build things like diodes and transistors. It's about tracing that path from, say, a pure silicon or germanium crystal.
Right, those elemental ones Feynman starts with. The diamond-like structure, tetrahedral bonds, four nearest neighbors.
Exactly. And how we go from understanding that basic structure to the devices that power everything, it really kicks off with temperature. At absolute zero, nothing moves. It's an insulator, pure and simple. All electrons are locked up.
But heat things up, even just to room temperature.
And thermal energy, $, starts shaking things loose. Some electrons get enough energy to break free from their bonds. And right there, you get the two main players Feynman introduces. The electron, the negative charge carrier we know and love, and this other thing, the hole.
The positive carrier. Okay, let's dig into that. How does an electron actually move through this crystal lattice? It's not just bouncing around like a billiard ball, is it?
No, not at all. It's quantum. The electron's movement, its energy is restricted. It can only exist in certain energy ranges or bands. We talked about this before, the idea of energy bands.
Yeah.
For conduction, the important one is the conduction band. That's the higher energy level where electrons can roam freely.
And we often see this visualized with that EK diagram. Energy on the vertical axis,
Right. What about
the
the
horizontal K, and Y the sort of valley shape.
Right, the EK diagram. So $1 is the wave number, basically related to the electron's momentum as a wave, that parabolic curve, that valley shape. It's super important. Its curvature tells us the electron's effective mass inside the crystal, how it responds to forces. A shallower curve means it acts heavier, a steeper one lighter. The point is, an electron needs enough energy, usually from heat, pay dollars, to jump up into this conduction band valley. Once it's there, it can conduct electricity.
Okay, so that's the electron. Pretty standard, negatively charged. But the hole, that feels like the really counterintuitive part. It's just a missing electron in the lower band, the valence band.
It is, and this is Feynman's brilliance shining through. When an electron jumps out of the valence band to the conduction band, it leaves behind an empty spot. Now, you could try to track the complicated motion of all the other billions of electrons in the valence band shifting around to fill that spot.
Which sounds impossible.
Practically, yes. But Feynman shows that if you look at the physics, the energy structure of that valence band, its own EK curve, is sort of an upside-down parabola, that empty spot, that absence of a negative charge.
Behaves like a particle itself.
Exactly. It behaves for all intents and purposes like a real physical particle. And it has two key properties.
It's positive, obviously, because it's the absence of a negative charge.
Right. And crucially, because of that inverted shape of the valence band's energy curve, it also has a positive effective mass. So we can treat this hole in our physics equations just like a normal positive particle moving around. It simplifies everything enormously.
And creating these electron-hole pairs, that takes a specific amount of energy.
Yep. It's called pair production. You need to give an electron at least enough energy to cross the gap between the valence band and the conduction band. That minimum energy is the energy gap, EGI. It's a fundamental property of the material.
And that energy often comes from heat, right? $?
Primarily, yes. In germanium, the gap is pretty small, about 0.72 electron volts. So even at room temperature, there's constant creation and recombination of these electron hole pairs happening naturally.
Okay, so pure crystals have some conductivity due to this thermal pair production. But the real game changer was figuring out how to control which carrier dominates. This leads us to doping.
Exactly. Doping is where we intentionally introduce specific impurities into the crystal lattice to dramatically skew the population electrons versus holes.
Let's start with making electrons the majority. That's normal type, for negative carriers.
For Noller type, we use what's called a donor impurity. A classic example is arsenic. Germanium has 4 valence electrons for bonding. Arsenic has 5. When you substitute an arsenic atom for a germanium atom, 4 of its electrons form bonds, but that 5th one is just extra. It's very loosely bound.
Doesn't take much energy to free it.
Hardly any. Much, much less than the main energy gap. Just a tiny bit of thermal energy, $88, is enough to kick it into the conduction band, ready to carry current. The arsenic atom itself stays put, having donated an electron, so it becomes a fixed positive ion in the lattice. But the mobile carriers are overwhelmingly these negative electrons.
Okay, so for a heterotype, we want positive holes to dominate. We need an impurity that takes an electron.
Precisely. We use an acceptor impurity, Think aluminum, which only has 3 valence electrons. When aluminum replaces germanium, it's short 1 electron to complete its 4 bonds, so it readily accepts or steals an electron from a nearby germanium atom's bond.
And stealing that electron leaves behind.
A hole, a mobile positive hole in the valence band. The aluminum atom, having accepted an electron, becomes a fixed negative ion. But the majority carriers available for conduction are now these positive holes, germanium.
So we can create material that's mostly negative carriers or mostly positive carriers, but how do the numbers balance out? Feynman brings in the mass action law.
Yes, this is crucial for understanding equilibrium. The law states that at a given temperature, the product of the hole concentration and the electron concentration is constant, N(P) a text constant times E.
What does that mean practically? If I heavily dope with donors to make lots of electrons, what happens to the holes?
The number of holes has to go down. See, thermal energy is always creating electron-hole pairs. But if you flood the crystal with extra electrons from doping, it dramatically increases the chances that any thermally generated hole will quickly run into an electron and recombine, essentially disappearing. So increasing NaN forces NeB out to keep the product NeP constant at that temperature.
But the answer never goes to absolute zero, right? There are always some minority carriers generated by heat.
Always some, yes. The minority carrier concentration is mostly determined by the temperature and that energy gap, through 120 volt. The crystal stays neutral overall.
Okay, we've got the theory. Electrons, the surprising positive hole, and doping to control them. But how did they prove the hole was real and positive? That feels like a big leap.
It was. And the proof came from a classic experiment, the Hall effect. Feynman explains it clearly. You take your semiconductor sample, maybe a little rectangular block, you pass a current through it, say left to right. Then you apply a magnetic field perpendicular to that current, maybe pointing down.
Okay, standard physics setup. Magnetic fields push on moving charges. The Lorentz force.
Exactly. Now, if your carriers are negative electrons, like in a nuller-type sample or just a normal wire, they're moving against the conventional current direction. The magnetic force pushes them sideways. This sideways push piles up electrons on one side of the block, leaving the other side positive. You get a voltage difference across the sides. That's the Hall voltage. We can measure its polarity, its sign.
So if the carriers were positive holes, moving with the conventional current,
the magnetic force would push them sideways, but because both their charge and effective direction of flow relative to the electrons are opposite, they pile up on the opposite side compared to where electrons would pile up. This creates a Hall voltage with the opposite sign.
So you run the experiment on a Boltzmann-type material, measure the Hall voltage.
And bingo! The voltage sign flipped compared to null R-type. It was definitive proof that the charge carriers in the type material behave exactly as if they were positive. It validated the whole Hall concept and the underlying band theory, a huge confirmation.
Fantastic. Okay, proof in hand, let's build something. We take our dollar-type and dollar-type materials and stick them together, the famous dollar junction.
Well, not quite stick them together. It has to be within a single continuous crystal structure. But yes, you create a boundary where dollar type meets a dollar type, and as soon as you do that, diffusion kicks in. You've got tons of electrons on the dollar side and very few on the dollar side, so electrons naturally diffuse across to the doll side.
And holes do the opposite, from tellers and dollars?
Exactly. High concentration on the taller, low on the dollar side, so they diffuse across to the dollar side.
But wait, when these carriers diffuse across, they leave behind those fixed impurity ions, right? The positive donors on the dollar side and negative acceptors on the dollar side.
Precisely. As the mobile electrons and holes diffuse away from the junction, they uncover these fixed charges. This creates a region right around the boundary that gets depleted of mobile carriers, the depletion region. But this region is now filled with fixed positive charges on the dollar side and fixed negative charges on the dollar side.
And separated charges create an electric field.
A very strong internal electric field, pointing from the positive dollar side charges to the negative dollar side charges. This field opposes further diffusion. It creates a potential difference across the junction, what Feynman calls a potential hill. This hill gets just steep enough to stop the net flow of electrons from dollars and holes from dollars to dollars. Equilibrium is reached, zero net current.
Okay, equilibrium. Now the fun part. Applying an external voltage. Let's do reverse bias first.
Yeah.
We hook up the battery to make the null side more positive and the teen side more negative.
Doing that effectively adds to the internal potential hill. You're making the barrier even higher.
So the majority carriers electrons from dollar holes from this dollar, they just can't climb that bigger hill.
Pretty much impossible. The current from majority carriers drops essentially to zero, but there's still that tiny trickle of minority carriers.
The ones created by thermal energy.
Yep. The few holes generated thermally on the dollar side find this huge hill is actually a downhill slope for them, so they slide over to the tie side. Same for minority electrons on the dollar falling down the hill to the dollar side. This tiny flow of minority carriers creates the reverse saturation current. It's small and mostly just depends on temperature because that's what creates the minority carriers, not so much the reverse voltage.
Okay, now the other way. Forward bias. We connect the battery to make the dollar side positive and the dollar side negative.
Now you're fighting against the internal potential hill, you're lowering the barrier.
And if you lower the barrier,
The majority carriers can start pouring across. Electrons from the dollar side see a much smaller hill and flow easily to the dollar. Holes from the dollar flow easily to the dollar side, and the relationship isn't linear. Because the number of carriers able to overcome the barrier depends exponentially on the barrier height, or lack thereof, the current increases exponentially as you increase the forward voltage.
exponentially. So a tiny change in forward voltage gives a huge change in current. That's the rectifier action easy flow one way, almost nothing the other way.
That's the diode. And notice that thermal energy term, Kli2 pops up again right in the exponent of that current equation. Propto EQ delta VKT day.
So the current is super sensitive not just to the applied voltage delta V dol, but also to temperature dollar.
Extremely sensitive. Raise the temperature, Kli gets bigger, the exponent gets smaller for a given voltage, meaning even more current flows. It highlights the thermal challenges in semiconductor design.
Okay, we have the diode. Now, the grand finale,
Yeah.
the transistor. Feynman describes the die-law structure, basically two junctions back to back.
Essentially, yes. You have three layers, emitter, base, and collector. Say, Boltzmann-type emitter, a very thin, Nollar-type base in the middle, and a type collector. The trick is how you bias the two junctions. The emitter-base junction is forward biased.
So it injects lots of carriers. In this diode case, holes from the bioemitter pour into the dollar base.
Loads of them. Now, the second junction, the base collector junction, is strongly reverse biased.
Creating a big potential hill, or rather a steep downhill slope, attracting those holes from the base towards the collector.
Exactly. A large electric field pulling holes across. But here's the absolute key, the design genius. The base region must be incredibly thin. Feynman gives a figure like 10⁻³ centimeters.
Why so thin? What happens if it's thick?
Recombination. Remember, the base is non-dollar type, full of electrons. If the holes injected from the emitter spend too much time diffusing randomly across a thick base, they'll likely bump into an electron and recombine. Poof, gone. No collector current. But if the base is thinner than the average distance a hole travels before recombining the diffusion length, then almost all the holes injected by the emitter make it across the base.
And then they see that big attractive field from the reverse bias collector junction.
And get swept right across into the collector. So the small current controlling the forward bias of the emitter-base junction determines how many holes get injected, and nearly all of those holes then contribute to a large current flowing out of the collector.
Tiny input current controls a large output current. Amplification.
That's the magic of the transistor, derived directly from controlling these carrier flows across carefully engineered junctions.
Amazing. So tracing it back, we went from the basic crystal lattice, understood electrons, and this crucial hole concept.
Used doping to create Nollar-type and Pyre-type materials, proved the hole was real with the Hall effect.
Combine them to make the tile junction diode, the rectifier.
And then stack them into the three-layer transistor for amplification. It's a beautiful logical progression laid out in the chapter.
And that thermal energy term, K dollar, was everywhere, wasn't it? Driving pair production, sitting in the mass action law, and critically in the exponent for junction current, making everything temperature sensitive. So here's something to chew on, thinking about that sensitivity. We mentioned germanium has a small energy gap, about 0.72 eV. Modern chips often use silicon, around 1.1 eV, or even gallium arsenide, around 1.4 eV. Based on everything we've just discussed, the mass action law, the exponential current dependence on EGaN and K dollar, how would using a material with a larger energy gap fundamentally affect a device's thermal stability and maybe even its potential speed?
Oh, that's a great question. It forces you to think about how EGA influences both the unwanted thermal carrier generation and the fundamental current flow equations. Yeah, definitely something to mull over.
It really connects the deep physics to practical engineering choices. Well, this has been fascinating. Thanks for walking us through the core ideas of semiconductor physics from Feynman's perspective.
My pleasure. It's foundational stuff, really rewarding to revisit.
We hope you found this deep dive useful. Thanks for joining us, and until next time.